Let's start with a little space trivia. If a curious kid came up to you right now and asked, "In our solar system, what planet has the most moons?" What would you say? If you asked a standard large language model that question, it would immediately generate a reply. Based on the parameters locked in during its training, it would confidently tell you the answer is Jupiter, with 88 moons. But science didn't stop on the day that AI finished its training. If you check a reputable organization like NASA today, you'll find the true answer is actually Saturn, which currently boasts 146 moons. That wrong answer exposes a structural flaw in how these models operate. First, they lack a primary source. The AI isn't looking up documents. It is generating text straight off the top of its head, completely untraceable to any verifiable evidence. Second, the data locked inside its parameters is frozen in time. As scientists keep discovering new moons, the model's internal memory becomes a snapshot of a previous reality, completely cut off from the current state of the world. These two specific issues, an inability to cite sources and a static memory, are the primary challenges of interacting with standard large language models. Without a mechanism to actively check the facts against a shifting reality, the system is forced to guess. It takes an incredibly capable generative engine and turns it into a highly confident liar. Fixing this problem required an engineering pivot. Instead of trying to build an entirely new, massive model from scratch, researchers changed how the existing model fetches its information. They developed a framework known as Retrieval-Augmented Generation, commonly referred to as RAG. If we set aside the generation part for a moment, we can see how the framework actually functions. The logic resides in that retrieval step. RAG achieves this by introducing a content store. This is an external, dynamic repository of data. It could be open information like the internet, or it could be a highly secure, closed collection of enterprise documents and internal policies. By drawing a line to that repository, we shift the AI's core source of truth. It no longer relies entirely on the static parameters it memorized during training. It relies on a verifiable, real-world environment. To see how this intercepts the hallucination problem, let's track a query through the new workflow. It begins exactly the same way, with a user submitting a specific question into the interface. Before any text is created, the system sends an explicit instruction to the model to pause. It is told not to generate a response based on its internal memory. First, the system takes the user's question and routes it down to the content store. It searches that repository to retrieve factual documents directly relevant to the prompt. Those newly retrieved facts are then pulled back up and combined with the user's original question. This creates a single, highly enriched prompt containing both the query and the exact evidence needed to answer it. Only after that data combination is entirely complete does the generative model process the prompt to produce an answer. By injecting hard evidence right before the text is generated, RAG ensures the AI's final answer is mathematically bound to reality rather than probability. This setup immediately resolves the out-of-date problem. When astronomers find another batch of moons orbiting Jupiter or Saturn, engineers don't have to spend massive amounts of time and computing power to retrain the underlying foundation model. Instead, administrators simply upload the updated information directly into the targeted content store. The very next time a user asks a question, the AI accesses the newest reality without a second of downtime. It also solves the sourcing problem. Because the AI is explicitly instructed to pay attention to external primary data, it can actually show its work, providing direct citations to the documents it used to construct its answer. This shift allows the model to recognize its own constraints. If the content store lacks the necessary data to answer the query, the model is instructed to simply state, "I don't know." There is an operational catch, however. A RAG system's accuracy is entirely dependent on the quality of its retrieval mechanism and the cleanliness of the data it connects to. If your retriever is flawed or your data is messy, the generator is starved of grounding information. A completely answerable question might result in a poorly constructed output simply because the system couldn't surface the right document. But when tuned correctly, RAG transforms an AI from a static oracle into a meticulous, evidence-based researcher. It anchors the generative power of large language models to verifiable facts, making them trustworthy enough to handle high-stakes, real-world applications.